First, I would like to thank the organizers for giving me this short-term opportunity. They asked me last week if I can present this as a talk, and well, I was a bit sick, so I said immediately yes, but I was sure I will come. But when I got, so to say, realized I should give a talk, I also noted, well, I don't really have anything to say on altermagnets, but I still have some thoughts, or we had some thoughts about it, and I would like to comment a bit on some works which have already been done and also add some own thoughts on that. But I also would like to add something else which is already published, which is not directly related to altermagnets, according to the definition given by the organizers here. Namely, I want to talk about singlet triplet mixing in Ising superconductors. This is a work which we did with some, especially Gao Mintang, who now moved to China. And it's published already, but I will show you that there are some important messages to take from this. So what is this about? I'm aware that probably most of the community here is not so much in superconductivity, and later I will have some slides which explain some very basic, try to explain some very basic things. So what is this Ising superconductors? Maybe it appeared already in some sense in the overview talk. There is this so-called spin-valley coupling in certain two-dimensional transition metal decalcogenites, so it's not related to a spin structure, but that's why I think it's still a bit related to, if concerning the electronic properties, to something which people call here altermagnetism. Namely, we have different polarization on different parts of the Fermi surface, which average out to zero if I average over the whole class. So they are, so to say, these conduction electrons are somehow polarized, but on average they are not polarized. And so this is described by a simple Hamiltonian like this, and so that's a effect has been. So what is the effect of such a internal magnetic field? Let me first remind you that superconductivity is generally destroyed if I apply a field which is given by roughly the pairing energy, so the binding energy of Cooper pairs in a standard way, but in certain certain crystals without symmetry centers, which is exactly the type I've shown you, noted already quite some time ago, one can have a strongly enhanced critical field. So this is this old work by Bulayevsky and co-workers, where they predicted that the critical field can, in some sense, it would even diverge at low temperatures. This is the Pauli critical field down here. Now, it has been realized, and that's why it was kind of raised a lot of interest in the last years in these materials, where they see, for example, here a suppression of TC by almost nothing for fields up to 11 Tesla, where you would, according to the standard estimate, already have vanishing TC. And even more convincing, there are tunneling spectroscopy data published just last year, where they could prove that they see signatures of superconductivity up to 30 Tesla in plane field, and that's kind of quite unusual. And now let me explain what this has to do with, or what is the origin of this. It's related to the spin structure of this materials, and namely the standard would be without a magnetic field. I have these two spin split bands, as I told you, and I just have pairing, but I always have, if I have an up spin on that side, I have a down spin on that side, so that's unusual because usually I have both available. Yeah? And this can be expressed in terms of the pair amplitudes, which are basically, say, I have an up spin at k, down spin at k prime, minus this was the opposite combination, but this I can decompose in a spin component, which is a singlet here, which is a standard Cooper pairing, but at the same time, I get with the same amplitude a triplet pair. Yeah, so due to this type of electronic structure, I get, although I have only S-wave pairing interaction, I automatically get a pair amplitude. I get Cooper pairs which are spin triplet, yeah, which just comes from this electronic structure here, and this is what I want you to remember. And then what we kind of did in that work was to look at what happens in an in-plane magnetic field. Then things become more complicated. We have to talk about non-collinear spins, which adds more pairing opportunities here, which all appear somehow and can be calculated. And then the surprising finding in that work was that we looked at the density of states. So what is the prediction for spectroscopy? And then we found this surprising mirage gap. So this is a superconducting gap here appearing at low energies of the order of delta zero, and in an in-plane field suddenly a gap opens up given by this internal pairing energy, this internal spin split energy beta, which is a signature then of this singlet triplet mixing and so on. And unfortunately, the experimentalists of the experiment I've shown spent some time looking for it, and they didn't find it yet. So, but we're not sure what's going on there. Okay, and at large fields, everything vanishes again. So this is basically my message here from a slightly different system, but that we have the singlet triplet mixing, which leads to spectroscopic signatures. Okay, one can also combine this type of systems, this kind of singlet triplet coupled superconductors into Josephson junctions by theoretically combining them in such a layer. Then we have a phase difference, a superconducting phase difference, and we have principle could have different in-plane magnetic fields, which are, for example, by proximatized two-dimensional ferromagnets or so, as a kind of theorist dream. And in that case, one can easily calculate the Josephson coupling, and what one finds is such a behavior of a critical current, which is just sinusoidal, but the critical current is modulated by this angle of these magnetizations. And at the same time, one finds a spin torque because one has a non-collinear effective magnetic fields here, which depend on the superconducting phase. And this is again something I want you to remember. So this kind of singlet triplet pairing or coupling leads to kind of a dependence, for example, on the critical current on the magnetization dependence. So this I1 is here proportional to that. All right, and well, that's actually, in some sense, pretty much I wanted to talk about things we have already done. I could talk more about this, but I see I'm kind of quite fast, but let's see. So if there, but maybe it's a good time also to ask you if you have any questions at this stage. You can ask them here, I mean, concerning this. Yeah?
Regarding to this kind of mirage gap that you showed in the previous slide, kind of the gap changes if you change the applied magnetic field.
Right.
It seems to kind of first open up and then close again. Is there an easy way of understanding how?
Yeah, it's very easy, very easy. Thanks for the question. So actually, you can actually calculate it. So the position is given by the square root of beta squared plus b squared. So this explains why the position, so to say, slowly moves up. So it always appears at beta, moves up. And then the width is given by this expression. It's proportional to the field, and it's proportional to delta divided by beta. But delta itself, due to self-consistency, this is in this plot, so to say, goes down. So that's why it, so to say, first goes up, and then it goes down, because in some sense it's completely dependent on the main gap, and then the main gap vanishes, it goes to zero. So at this bx, everything goes to zero here. Yeah. Yeah.
Yes, for pedagogical purposes, I would maybe highlight that the Ising splitting is time reversal symmetric, so the spin is opposite at k and k prime. So in that sense, it's very different.
It's very different, yeah, but let's say from the electronic point of view, you know, you average over all k direction and you have zero, zero spin. I totally agree that it's a completely different class of systems and so on. But I just want to point out that you get, due to this spin polarized band structure, you get a singlet triplet mixing, yeah, and that's exactly what I'm kind of will discuss later. Yeah, okay. Okay, let me now share with you some thoughts on this actual title, where we don't really have any. I can show you a calculation which I did over the weekend. Well, I also work on weekends, yeah, so I'm not sure whether the students who stop working on Friday afternoon, what's going on there.
That's probably illegal and not in German.
And I want to point out that we started this, I started to think about this together with a postdoc, Alexander Svetogorov, who joined my group some months ago, and then I kind of said, look, this looks like an interesting problem, let's discuss it. And then we had some discussion, so he was involved in most of the points I want to make. And I want to, so there are these several keywords, Andreev reflection and ferromagnetism. Again, I assume most of you have maybe sometimes heard of Andreev reflection, but maybe sometimes not. Let me explain you very basic what it is. So Andreev reflection is the following process. If I have a superconductor, I have a gap, so I have no quasi-particles below this gap energy. If I want to inject an electron, it can still go in the superconductor, but it has to form a Cooper pair, which results in the fact that I get a reflected hole. That's why it's called reflection. In reality, it's actually two particles going from the normal metal ferromagnet into the superconductor. It's just some kind of convenience to call one thing a hole, right? So this is this process. And so this can happen at subgap energies. And for example, you already see one has to inject an electron with upspin and a hole with downspin if you want. Now, there's a matter of what up and downspin here means, but one is in the up band and one is in the downspin band, if you want. So it's proportional to these transmission probabilities. But of course, if these transmission probabilities are not unity, there's also some reflection probability which leads to such processes. So electron comes in with up, then it's Andreev reflected as a hole, but then the hole is not going back to the other side, but it's again normally reflected, again Andreev reflected, again normally reflected, and again Andreev reflected, and finally it has turned into a hole in the down band and can come up out on the other side. Now you can easily imagine that I can continue this series, and it's a simple geometric series of amplitudes, right? So I just sum up everything. Oh, by the way, this gamma is an energy-dependent parameter, which is it has unity, absolute value below the gap, yeah? But above the gap, it will just go to zero somehow. So basically this leads to this simple formula for the Andreev reflection probability, which is exactly summing up this geometric series and taking, because it's an amplitude, for the probability I take the square of this. So it's a little bit complicated looking formulas, but it has a very simple interpretation. And now comes the question, what has this to do with the ferromagnet? Well, you first see that it depends on the transmission probability in the down band and the transmission probability in the up band. So it will be sensitive to the spin polarization in such a contact, right? And there's furthermore a very interesting thing that it depends on the relative phases of these two reflection probabilities, which might also play a role. Now the fact that Andreev reflection is sensitive to spin polarization is a topic which has been much discussed like 20-something years ago, where people looked at this with simple ferromagnets and superconductors and tried and I found actually by one of our speakers here a quite interesting paper by Ingo Mazin on this from that time. Basically, there are many papers. I just took this one. So basically what you find is that normally the Andreev, because Andreev transports two charges, the conductance is doubled. And if you assume that the polarization is only 50%, so these transmission probabilities are different, it is reduced by some factor, the conductance, right? This is a calculation here from that paper, and you find similar calculations in other papers around that time. So the Andreev reflection probability is reduced, right? And furthermore, there are some other effects which, for example, you can have simply a bad interface, which also reduces this, and then you also have a reduction here, but you have a slightly different dependence here. Yeah, maybe it's not the best, but I just wanted to point out you get a reduction here of the Andreev conductance due to a finite polarization. But it's difficult to distinguish from just a reduction due to in a bad interface or some kind of normal reflection. And there are many variants of this. So this is not the only way. And I also want to emphasize that there's this interesting phase dependence which can lead to some subgap resonances which appear, okay, so this should be phi s here, so this phi here, which appear at subgap resonances, which basically I just wanted to highlight that, you know, in principle, Andreev conductance is a very sensitive tool to investigate something about the interface. Now, since I submitted the abstract, two papers appeared already on Andreev reflection. So one 2 months ago, one just appeared today on the archive. And basically, I can explain you now, based on that picture I have, what's going on. So this is now the simple model of the altermagnet. Yeah, so you just take a spin polarization which has this D-wave shape, and for me this was the original motivation. I say, okay, that's the simple Hamiltonian. I don't need to do any complicated band structure calculation or whatsoever. I can just take this Hamiltonian and plug it into my scattering theory and look at what's going on. Yeah, and that's what they actually did. Yeah, and this is the light. Okay, it's not, unfortunately, not very well visible here. So these are then the results of this paper, or this is kind of the sketch. So they look at the altermagnet superconductor interface. The superconductor can be S-wave or itself a D-wave. Let's drop this D-wave here for the moment. And then they look at these two different orientations of this altermagnet, which is the first one. A is like this one, and B, in that case, it's turned by 45 degrees. And this is the result of the calculation. So this is now the Andreev conductance. Alpha is this altermagnet parameter, which is a dimensionless quantity, and this is the voltage, and they have these two kind of behaviors. In the A case, this is this one here, the conventional. We see that this altermagnetism, it has actually only very little effect on the Andreev conductance. In contrast, in the other case, it has a stronger effect. And that's actually not surprising after I told you, because basically the interface, you know, this is the interface, so the dominant transport is in this direction, and in this direction, obviously the polarization is essentially zero, right? But of course, if you average over all directions, some things remains, but that's why the effect is small. But here it's much larger, right? Because here I have, so to say, in this direction, the full polarization, and I see a larger suppression here. Okay, so that's basically my summary. So I kind of, in some sense, I found after reading this paper and so on, I said, okay, maybe it's in the end not so interesting, because it's really everything just explained by the polarization of the Fermi surface. But and I don't know how realistic it is to change these directions, but I just saw there are these samples where you rotate this thing, so maybe it's interesting, yeah. Yeah, okay, so that's, there are more things to say on this, and I don't want to say it here now. Okay, now let's talk about supercurrent. Supercurrent and ferromagnetism. Basically coming to this, which I already mentioned to you, by the way, so that there's a famous work by Fulde, Ferrell, Larkin, Ovchinnikov in the 60s, who considered the spin split superconductor, and they showed that because you have, if you plot the Fermi surfaces, you have seen these pictures all over here already, and if you now at superconductivity, you want to pair this electron and this electron, and now you see, because the Ks are different, they have a finite momentum, so that's why you get a finite momentum proportional to the exchange coupling, and because you have not only this pair here, but of course you have the one which just pairs the opposite one, so you, so to say, do not get a finite momentum of the whole superconductor, but you end up with zero momentum, but you still can get something like a standing wave, which is this order parameter oscillations predicted but never really found convincingly in reality, because it's, for example, sensitive to disorder. Now, this is an interesting way to understand the effect on the Josephson effect. So the Josephson effect, as all of you know, is the effect if I have two superconductors with a phase difference. I have a phase-dependent energy, and I can basically have a current, which is the derivative of the energy with respect to phase, which is just sine phi. I've shown you this before. Now, and just to give you a simple picture to explain what's going on with the ferromagnet, this is the energy, and this is the phase, current phase relation. Now, if we add a ferromagnet, what happens? So we add some finite length ferromagnet. Well, then, in some sense, this Q comes into place. So there will be a phase shift, which is proportional to this Q times the length here. This basically means I can basically shift this cosine. I once shift it to the right, I once shift it to the left, and then I take the average. And then I get again a cosine, which is a green curve with a smaller amplitude, right? And this basically means I get a reduced supercurrent, and basically just doing a little bit of algebra here, I get that the current phase relation is sinusoidal, but the critical current now depends exactly on this phi f parameter. So this is just a very, very simple picture, and it depends. So, and the interesting thing is, so it depends like cosine phi f. So it oscillates as a function of phi f. Of course, the critical current in principle is always a positive quantity. But of course, in principle, if it's negative, I just measure the current, the maximal current in the other direction. So I get this 0 pi oscillations of the critical current, which were first again by the same Bulayevsky, who already appeared earlier, discussed in this work. Okay, and again, now I take the words which appeared while we were kind of not too much discussing about it, but anyhow, so there are the same group. By the way, in initial program I saw Jakob Lindner as a speaker, if I'm not mistaken, but now he is not here. Would have been interesting to discuss, and then I would have probably given another talk or no talk at all. Okay, anyhow, so they looked at this numerically, basically solving the Bogoliubov-Duhem equation for such a system. Normal metal here is actually an altermagnet, so either this direction or this direction. This is their parametrization. And in the end, what they find is that the supercurrent, as a function of the length, in one case shows oscillations, and in the other case doesn't show oscillations. So straight junction is this one. It doesn't show. It shows an oscillation which is basically signaled by the 0 pi transition here. And around the same time, another paper appeared here, who also looked at a finite Cooper pair momentum, and they found this oscillations of the critical current as a function of chemical potential here, or the length. And again, all these formulas can in some sense be I mean, not the decay, but at least this oscillation can be captured by such a formula where this altermagnet parameter appears as this ferromagnetic phase shift and depends on the length. Okay, so that's, so to say, a repetition of what has been done in the theory. Now comes my own calculation. I was then thinking, so what can we do which is really something different? And I just considered the following question. So let's assume, and this is pure theory assumption, that we have an altermagnet in close contact with a superconductor, and both are thin, so to say. They both influence each other so that I can effectively describe them as a single system which has an altermagnet exchange coupling. And that's actually the new thing here. So I have an exchange coupling which depends on the direction. I mean, it's not new, but for superconductivity, it's something which people usually do not consider. And I just add a superconductor, leaving out all kind of kinetic energy terms. So I just have this term. And then that's the advantage of working with quasi-classical theory for many years. Then I already basically know how the Green's function look like, and that's the calculation I did. So basically I can calculate the full Green's function of such a system, and which now contains this direction-dependent exchange coupling, so it has some form here. It has this equilibrium, so it has a Masubara frequency, it has this delta. And so what is interesting here is that one can actually see from these formulas that this has an unusual superconducting pair amplitude. This is exactly what I mentioned before. So in that case, as you know, or some of you might know, order parameters, superconducting order parameters are characterized by an orbital degree of freedom, like S wave or D wave. They can have a spin structure, spin singlet or spin triplet. Now in this notation, the singlet is I sigma y and the triplet is this. And it has a time which is signaled by the question if this is even in omega n or odd in the frequency. So there's odd, so-called even frequency is the standard, and odd frequency pairing is possible. And what you can see from this formula here is that the altermagnet induces a spin triplet, D wave, odd frequency order parameter. And that's for those people who are in superconductivity. Okay, I see people taking photos. Yeah, please don't publish them before we do something on this. Yeah. I don't know. Maybe it's not interesting enough. Yeah. So it has both. Yes, yes.
If you take odd frequency, you should be able to generate triplet S in altermagnet as well.
Yeah. But I'm just was fascinated by this kind of, that you simply get a D wave order parameter, but maybe it's not so surprising for you. Well, that's what comes out, and I haven't really followed this calculation. But I think in that sense, that's more or less what I find here, and you find other components again. So this is all very preliminary. Of course, one has to calculate this in a more realistic model of this coupling. One has to do this self-consistently, and so on and so on. But what is interesting is that we can, of course, calculate all the spectral quantities like the density of states, and that's again something which I would like to advertise if somebody can, kind of make this kind of spectroscopy on a superconductor, altermagnet, a heterostructure, even just with films on top of each other, it could be an interesting thing to study. One can, so to say, calculate from this how the spin split density of states looks like, which will be non-standard because we do not have a constant spin splitting. We can also look at the proximity density of states, so on the altermagnet side, and there are lots of predictions that odd frequency pairing leads to anomalous paramagnetic responses, and since the triplet pairing, one also sees the spin susceptibility, for example, if one can measure this, I don't know. And so this is what, so to say, our plan is to do here, is to now do this calculation more with more details, with full numerics, and calculate various structures. So one can look at different combinations where either one of them is a bulk metal and then a thin layer or otherwise. But this is something I would also really, like to get. If you with all the experience of what material can be grown on what, I would be really interested to learn what is possible here. All right, and that's basically my kind of here, so to say, suggestion for further discussions. Now I would like to thank my collaborators here from Konstanz, PhD student, and Alexander Svetogorov on this part, and these other people who once were in Konstanz, now in different places, or once were in Basel. I would like to thank all of them. And this is just a summary to say that, well, this kind of leads to this spin split dispersion relations, even if they have no net magnetization, might lead to interesting singlet triplet coupling, and I think that's something one can explore here. And so it's actually not so complicated for experts like Igor Mazin. He already knows all the results. So thank you for your attention. Well done.